Glider 4-2 Flight Instruments. Alright, let's take a stroll through the mystical world of altimeters. These instruments that serve as our wise height measuring companions in the realm of gliding. Picture this. A flexible plastic tube connecting the altimeter's static pressure inlet to those charming static portholes on the side of your glider. Now, when this altimeter is all set to the local pressure, its needles and dial transform into storytellers, revealing your majestic height above mean sea level, MSL. But, my dear aviators, the key to this tale lies in understanding atmospheric pressure, that force exerted by the air column above us. At sea level, it's like a robust bouncer throwing a punch at 14.7 pounds per square inch, or 29.92 inches of mercury if you prefer the poetic units. As you climb to the lofty heights of 18,000 feet, that punch dwindles to half its strength, a mere atmospheric shadow of its former self. Now, imagine the altimeter as a learned barometer, an aneroid philosopher, tapping into static pressure to unravel the mystery of your altitude. As you gaze upon the dial, those clockwise numerals from 0 to 9 tell a tale. The altitude detectives, the hands, point out the details. The shortest one speaks in tens of thousands, the middle in thousands, and the longest in hundreds, each divided into 20-foot chapters. But here's the catch. For the altimeter's storytelling to be accurate, we need a harmonious trio. Sea level barometric pressure at the standard 29.92 inches of mercury, a free air temperature of plus 15 degrees Celsius, or 59 degrees Fahrenheit, and the graceful dance of pressure and temperature changes with altitude. Since our atmosphere is quite the unpredictable artist, we employ a nifty trick, the altimeter setting. It's like the magical incantation that adjusts the local station barometric pressure to sea level, ensuring our altimeter spins a tale true to the skies. Now we will explore how non-standard pressure and temperature can impact flying, especially when it comes to adjusting altimeters. Without proper adjustments, flying could be risky. For instance, if you move from a high-pressure area to a low-pressure one without adjusting the altimeter, the glider's actual altitude is lower than what's shown. Conversely, going from a low-pressure area to a high-pressure one makes the glider's actual altitude higher than indicated. Thankfully, these errors can be fixed by setting the altimeter correctly. In local flights without ATC communication, there's an alternative, setting the altimeter to 0 on the ground, reading above ground level, AGL. But for longer flights or from higher airports, this might not work due to the excessive Kollsman window setting. Also, changes in air temperature affect the altimeter. On warm days, the air is lighter, raising pressure levels, and making the altimeter show a higher level for a given altitude. Now, let's talk about adjusting the altimeter. There's a window called the Kollsman window, and we use it to set the altimeter based on atmospheric pressure. There are 3 settings: QNH, QFE, and QNE. QNH is for mean sea level, MSL, QFE is for above ground level, AGL, and QNE is for flying above 18,000 feet. Glider pilots use QNE for wave flying above that altitude. Setting the altimeter to read the field elevation is a good check to see if it's working right. As we fly, it's crucial to adjust the altimeter based on the current setting. If we're over high mountains, the altimeter might show a higher altitude than what's real. So, it's wise to keep some extra altitude for safety. Let's look at a practical example, a cross-country flight. Before takeoff, we set the altimeter to the local setting. During the flight, we get new settings from different stations and adjust accordingly. Adjusting the altimeter is a big deal. If we mess it up, we might land at the wrong altitude. Even a small difference in altimeter settings, like 0.25 inches of mercury, can mean an altitude error of 250 feet. There are 2 ways the altimeter can show the wrong altitude. One is due to changes in air pressure, and the other is mechanical, controlled by the Kollsman window. In a nutshell, understanding and adjusting the altimeter is crucial for safe flying. Pilots need to deal with pressure and temperature changes to make sure they're at the right altitude. So, whether you're flying locally or on a long journey, keeping an eye on your altimeter is key to a smooth and safe flight. Understanding the altitude of a glider is crucial for pilots for various reasons. It ensures the glider is flying at a sufficient height to clear terrain or obstacles along the planned route. This is particularly important when navigating around mountainous areas, where pilots need to be aware of the glider's altitude in relation to the surrounding terrain. Altitude knowledge is also necessary for calculating true airspeed, TUSH. Altitude, in essence, is the vertical distance above a reference point or level. There are different types of altitudes, each measured from specific reference levels, serving different purposes for pilots. Let's explore the 4 types of altitudes that impact glider pilots. Indicated altitude. This is the altitude directly read from the altimeter without corrections. It's used for maintaining terrain and obstacle clearance and estimating the distance the glider can glide over the terrain without lift. The altimeter is set to the current altimeter setting, QNH, for accurate readings. True altitude is the true vertical distance above sea level, MSL. It's measured above a standard datum due to the shape of the Earth. Properly set local altimeter settings make indicated and true altitude synonymous. Absolute altitude is the vertical distance above the terrain, specifically above ground level, AGL. It's crucial for determining when an landing not at the intended airfield, must be performed, especially when lift is insufficient to stay aloft. Pressure altitude is the altitude indicated when the altimeter setting is adjusted to 29.92, considered the standard datum plane. It's used for various computations, including density altitude, true altitude, and tush. Density altitude is pressure altitude corrected for non-standard temperature variations. It serves as a measure of air density, impacting glider and engine performance. Higher density altitudes, often occurring in warm weather, result in longer takeoff runs, slower climbs, and extended landing rollouts due to higher ground speeds. It's important to note that pressure altitude and density altitude are the same under standard conditions. However, when temperatures deviate from standard, density altitude differs from pressure altitude. This distinction is crucial as density altitude significantly influences glider performance and the functioning of tow planes and power plants in self-launching gliders. If you click like and subscribe and leave a comment, we will provide a coupon for a free PDF download, one of 9 ebooks. However, each individual can only download up to 1 out of 9 ebooks for free.